Is Benjamin Rosenzweig, ZID 5644315, and this is my final experiment video discussing my results for understanding the solar system. I'd first like to start off by talking about Kepler's three laws. His first law, the law of eclipses, states that the orbit of a planet around the sun takes on the path of an eclipse with the sun being one of the two foci. This means the distance between a planet and the sun will change during the course of its orbit. Kepler's second law, or the law of equal areas, states that a planet will cover the same area of space over the same amount of time, no matter its position in the orbit. Despite the changes in speed as a planet is closer to or farther from the sun, the area it covers over a given period of time will be the same. Finally, Kepler's third law, or the law of harmonies, states that a planet's orbital period is proportional to the size of its orbit. This shows that planets farther from the sun take longer to orbit in an exponential ratio. In this photo, you can see the first scenario I investigated, in which a planet and moon orbit. In this scenario, I was able to clearly observe that as the moon orbited the planet wobbled slightly. This is because the Earth moves in a small circle around a point called the barycenter, the shared center of mass between Earth and the moon. Because of Newton's third law, both bodies pull in each other equally, so they both orbit this point. Since Earth is much more massive, the barycenter sits closer to Earth, which is why Earth's orbit is smaller and tighter than the moon's. This planet and moon simulation is very different from the situation in question 1, where the barycenter between the star and the planet is really close to the star. If we consider the planet and star to be Earth and the sun, then the barycenter is located about 450 kilometers from the sun's core. That's because the sun is so massive, around 333,000 times the mass of the Earth. Simulation in question 4, I explored a scenario in which I increased the original mass of the planet by 1.5 times. The center of mass of the barycenter in this scenario is located slightly further away from the sun relative to the simulation in question 1. However, the change in barycenter distance from the sun is extremely minimal, as the sun's mass is still significantly larger than the planet. Finally, for the scenario in question 7, in which I increased the mass of the sun, the barycenter was located much closer to the sun's core. As the planet orbits the center of mass, the gravitational force of the sun coupled with the closer proximity of the barycenter created an orbit in which the Earth crashed into the surface of the sun. The key difference between the barycenter locations for the planet and moon simulation and the planet and sun simulation is the mass ratio. The sun is way more massive than the Earth, so the barycenter sits near the sun's core and its wobble is tiny. But with the Earth and the moon, the mass difference is smaller, so the barycenter is farther from the Earth's center, causing a more noticeable wobble. Next in the experiment, we looked at a to-scale simulation of the Earth and the sun. We know that the total distance between the Earth and the sun is 1 astronomical unit. Thus, as a planet starts 2 grid squares away from the star, we can assume that each grid square represents half an astronomical unit. Next, I changed the distance of the planet and the sun and measured the time it takes each planet at those orbital distance to complete one orbit. For this scenario 1 photo, the planet distance in AUs is 0.5 AU, and the orbital period in Earth days was 138 days. For scenario 2, the planet distance was 1.5 AU, and the orbital period in Earth days was 563 days. For scenario 3, the planet distance was 2 AU, and the orbital period was 836 Earth days. Finally, for scenario 4, the planet distance was 2.5 AU, and the orbital period was 1,283 Earth days. The data table looks as such. So do these results follow Kepler's third law? Well, going back to the third law, we know that a square of a planet's orbital period is proportional to the cube of its average distance from the sun. Since the square of the orbital period is proportional to the cube of the distance, a small increase in distance leads to a much bigger increase in orbital time. Even if the numbers aren't exact, our results still match Kepler's third law. Next in my experiment, looking at orbital velocity in our solar system, I would expect that Mercury, closest to the sun, would have the fastest orbital velocity, while Neptune, farthest from the sun, would have the slowest orbital velocity. According to Kepler's third law, planets further from the sun take longer to orbit and travel at a slower speed to maintain their gravitational balance. When looking at the orbital velocity equation, velocity is inversely proportional to the square root of the distance to the sun. This shows that the closer a planet is to the sun, the faster it has to move to resist the sun's gravitational pull. Thus, planets closer to the sun travel faster, while planets farther away travel slower. From this experiment, I learned that a planet's orbital shape and speed is entirely dependent on the gravitational pull of the celestial object it is orbiting. Gravity is the center of a solar system's function, and gravity and mass are essential in understanding how objects in our solar system move relative to one another in a functioning and organized way. I gained a deeper understanding of the physics of our solar system, and I look forward to learning more in the future. Thank you.